Okay, so welcome to our next speaker, Maxime Fairon from the Institut de Mathématiques de Bourgogne in France, who is going to speak to us about double Poisson algebra cohomology. Over to you, Maxime.
Exactly. Thank you very much for the introduction, and thank you to the organizer for inviting me to speak at this non-associative day. And I will first do a bit of advertisement. So maybe some of you have already received an email from Ivan a few hours ago saying that there was the official launch today of the Journal of Non-Associative Structures. So I hope this will be a great success, and feel free to submit your next papers to this great new journal. Okay, so now back to my talk. Let's talk about these double Poisson algebras. And so that you understand what I'm going to do, I will start with a general motivation and try to tell you why I'm doing that, and then also explain some classical construction of cohomology related to Poisson algebras. And after that, I will go to the non-commutative setting, explain what are these double Poisson algebras, and give you a first cohomology theory. And next, I will explain to you many other cohomology theories. So we will see how much of that we will be able to see. But just in case you are interested in that, everything is already on the arXiv. It's a paper with Daniele Valeri, my co-author, who is in Rome. And it was a great thing to write this with him. I really enjoyed doing this, but it's a bit of a long paper, so I will only be talking about the first part of it, and there is already many nice results to talk about. Also, okay, so let's just recap a bit some basic definitions so that we are all on the same page. So we start with classical Poisson cohomology, and in case you need it, just remember that if you fix a commutative associative algebra over K, K will be an algebraically closed field of characteristic 0 for me, but at the moment, you take whatever you want. So you fix such a commutative associative algebra, and then you have a Poisson algebra if you have a linear map from the tensor product of A with itself to A, which is such that it's skew-symmetric. Okay, so you exchange two arguments, you get a minus sign. You have Leibniz rules, so derivation rules in both arguments, and because everything is commutative, they look exactly the same. And finally, you have your Jacobi identity that I've written in some way, but you can write your Jacobi identity in the usual way using the skew symmetry. Okay, so what can you do with this? Well, with this, you can do the following. So you can first define what are here these curly x n of A as being the multi-linear vector fields on A. Okay, so these are skew symmetric maps. That's why they are homomorphism from the wedge n of A to A. These are skew symmetric maps that are k-linear, and they have some Leibniz rule in each argument. Okay, so the Leibniz rule is just the usual one you would think about. Right. And so what can you do on this space of multilinear vector fields? Well, you have your Chevalier-Eilenberg differential that I've written here. And why am I calling it like this? Because, I mean, if instead of this x and a, you were omitting the derivation rule that I've written here. So if you omit this derivation rule, then basically you can just look at homomorphism in for A being just a Lie algebra in some module, and you can basically rewrite this. Okay, so here it's just that in the first term, you would have the action of xi on the module, and then the formula is the same. Okay, so what is nice with that is that from this Chevalier-Eilenberg differential, you can define some homology, okay? And, well, in fact, a cohomology. And so this is a first way to do the Poisson cohomology as this Chevalier-Eilenberg cohomology of A. Okay, so there is a second way to do this. How does it go? Well, you start with the so-called quaternion noise bracket on your multilinear vector fields. Okay, so I mean, if you really wanted, the definition is there, but just remember that it's a way to get a graded linear map of degree -1, meaning that it's taking an element of degree k, an element of degree L, and it's giving you something of degree k plus L minus 1. Okay, and it has some nice property because this is, as I was saying, a graded Lie bracket. Okay, meaning in particular, and this is what is important, that you have this graded Jacobi identity that is written there. So why is this graded Jacobi identity useful? Because, well, if you take x is equal to y, okay, then you see that, okay, if you take x is equal to y of degree 2, okay, then you see that the left-hand side gives you twice the bracket of x with the bracket of x with z equal to something, and this something, when x is equal to y, if the bracket of x with itself is 0, then you in fact get the condition that you have a square zero differential on your complex. So this is the usual thing that you can do to play with the Poisson cohomology more from the bivector point of view, where you take, as I was saying, an element of degree 2 whose bracket with itself is 0, and from there you get a differential. And using this differential on your complex, you can define the corresponding cohomology, which we will call the Poisson cohomology of A. So again, this is very standard, and just a thing to keep in mind is that this is equivalent to what I was saying on the previous slide, okay? Because if now you define the Poisson bracket in the sense of the previous slide, or in the sense of the previous slide as being this multilinear map pi applied to AB, then you just identify the two differential, and these two cohomologies are just the same. Up to possibly a sign, I don't remember, but I mean, the cohomology will be the same. It's just the morphism of complexes that may be changed by a sign, but it's not important. Okay, anyway, so this is the thing that we should keep in mind, that you have these two notions of Poisson cohomology, because this will show up later in the talk, but I wanted to remind you of this construction. So let's now try to go to the non-commutative setting by seeing the Concevic-Rosenberg principle. So this will be the leading principle for my talk. The idea will be that these two Poisson cohomologies that I've defined, well, that I've recorded because they are very standard, we will want to obtain them through some representation factor that I will now explain. Okay, so it's really a general idea to get new mass that Concevic and Rosenberg have introduced, and their point of view was the following. So I'm slightly rephrasing, but what they've said is the following. Okay, whenever you have an associative algebra over some field K, which again for us will be of characteristic 0 algebraically closed, whenever you have such an algebra, an associative algebra, for any n, you can find a corresponding commutative associative K algebra that we will call curly AN here. And what is this thing? Well, this is the coordinate ring on the nth representation space of your algebra. So basically, you should think of this AN as being generated by symbols. These are these Aij here. So you should think of them as having some matrix labels I and J, and then the A is just an element in your algebra. Okay, and these matrix symbols, you should think of them as being functions on the representation space of the algebra, meaning that this representation space just encodes all representation of your algebra on a vector space of dimension n. Okay, and the nice thing for me is that this coordinate ring of your representation space, you can really define it by generators and relations as I've written there. Okay, so see the important relation in some ways, the last one, which tells you that the Ij entry of a product of your two elements in the algebra A, it's basically the matrix multiplication of A and B. And then you take again the Ij entry of this matrix multiplication. Okay, anyway, having said that, so we have this very nice functor that goes from associative algebras to commutative algebras, and the whole Concevic-Rosenberg principle is the following. We should, for any usual property P that we like on commutative algebras, try to find a new property, this P non-commutative on A, such that whenever we have an algebra with this property P non-commutative, we can induce under the representation functor the usual property P on all these representation algebras. So this will be the guiding principle for us today, because I will first recall some construction of Vandenberg, which will define some non-commutative version of Poisson algebras, which induces a Poisson bracket on representation algebras, and then we will lift that to Poisson cohomology. All right. Basically I've explained what is in this question. We want to induce Poisson cohomologies in the sense that I've recalled from something on non-commutative algebras. And here, maybe you would be able to say to me that, okay, everything I'm working on is associative, but remember that your Poisson bracket or a Lie bracket in general, this is non-associative. So I have in some way an associative background on which I'm adding some other layer, another non-associative operation. Right. So now that you have seen back the classical construction of Poisson cohomologies and the motivation, this Concevic-Rosenberg principle that tells you that you should be aiming for defining a non-commutative version of some nice structure like a Poisson bracket or its Poisson cohomology, we want to put that back at the non-commutative level. So to do this, we will be really working a lot with construction due to Michel van den Bergh. So what did he do? So just so that we are all on the same page, just keep in mind that this A from now on will be a unital associative finitely generated algebra over our algebraically closed field of characteristic 0k, and all my tensor products, they will be tensor product over the field. Okay. And so what did van den Bergh said? Well, he defined an operation, a double bracket, as something that I will tell you now, and you should just keep in mind for this notion there of double bracket that we want something that is a non-commutative version of an antisymmetric biderivation. So we need some skew symmetry rule and we need some derivation rules. This is what is there. But before saying more, I need to emphasize something with this definition. So a double bracket, according to van den Bergh, will be a k-linear map, okay, written like this as a double bracket, going from the algebra tensor itself. So far, it's as in the usual setting. In the usual setting, you would go from A tensor A to A. But see here, we don't land in A tensor A just, we land in A tensor A. Okay, so we need to be very careful. That's the big difference with the usual notion of Poisson bracket. And now we need to understand what is skew symmetry. Okay, so the first thing, if you were to write the skew symmetry in a naive way, you would say, well, we have an operation. Skew symmetry means that we swap the two arguments, we put a minus sign. Okay. In the setting here, it's almost the same thing. It's just that we need this extra tau12 here, which is an operation that is permuting tensor factors. Okay, so I mean, this is something that showed up a lot in the previous talk, so you are all used to that. But just keep in mind this notion here of cyclic skew symmetry, which is like the usual skew symmetry, but you need also to swap the two tensor factors because our operation lands in the algebra tensor itself. That's very important. So this is the first thing. And now the more important and nice thing is to understand the derivation rules. Okay. So the first derivation rule looks like nothing. Okay, so I'm writing it there. If I'm taking the double bracket of A with the product BC, I want the B to come to the left. And as you see here in the first part, the B will come to the left and multiply on the left the left factor of the tensor product, of the double bracket of A and C. And then the C needs to come to the right. And as you can see here, the C is coming to the right and it's multiplying on the right factor of the double bracket AB. Okay. So be careful about that. The order in which you are multiplying on the left or the right, it's important to know which tensor factor you are multiplying on the left or on the right. Because when you impose this auto derivation rule, so it's called auto here because basically this derivation rule is with respect to the auto bimodular structure, which multiplied on the left factor of A tensor A, and on the right factor of A tensor A. But look, because our cyclic skew symmetry, when it's permuting the two arguments, it's also permuting the tensor factor. The cyclic skew symmetry is telling us that the derivation rule in the first argument should be also adapted. And as you can see here, when I'm taking the double bracket of the product AD with the element B, the A will come outside and multiply on the left the right factor. Now, be careful about that. While the D will come to the right and multiply on the right the left factor of the double bracket AB. So here this is called the inner derivation rule because it relies on the inner bimodular structure, because as you can see here, the A is coming inside to multiply on the left the right factor, and here the same, the D is coming inside to multiply on the right the left factor of the double bracket. Okay, so with this we have the notion of a double bracket, which has a cyclic skew symmetry and some derivation rules. But what is important when you have a Poisson bracket is your Jacobi identity. And here for double Poisson bracket, you will have some kind of double Jacobi identity. So what does it mean? Well, you should keep in mind that your double bracket is going from A tensor A to A tensor A. So when you want to write a kind of Jacobi identity taking as an input 3 arguments, it should give you as an output 3 arguments as well. Okay, so this is why this double Jacobi, as I'm calling it, is going from A tensor 3 to A tensor 3. And now, well, I mean, this is the definition. I will not take too much time to see it, but you should just keep in mind that when you want to apply, for example, the double bracket of A to the double bracket of B with C, when you want to make this, well, you need to see if you choose to apply this double bracket of A to the left or the right factor of the double bracket BC. And for the definition, what we use is that we always apply it to the left factor. Okay, so this is what you have here in this notation here at the bottom, is this double bracket with a L as a subscript, means that you apply it to the left factor of a tensor product. Yeah, and with that you can write this kind of a double Jacobiator, and as you can see, it's kind of a cyclic permutation of the first term. But keep in mind that, for example, when you permute A, B, C cyclically, you also need after that to permute the tensor factors. Okay, so here in some way, when you have A, B, C, here you move your BC, your ABC to the left, and then here this tau 1, 2, 3 is moving them to the right. And here the same, if you look, you go once more to the left for the arguments here and once more to the right for your tensor factor. Okay, so these are the rules. I mean, if they look a bit weird, then let's forget about that. We will, I will not use that too much. You just need to keep in mind that the double bracket has a skew symmetry rule, 2 derivation rules, and a kind of double Jacobi identity, which is the vanishing of this last operation. That's it. Okay, and as a side note, in case there are some experts in the room, I don't know, but everything that I will do will be done k-linearly. But for example, if your algebra is an algebra over some subalgebra B, you can also do some bilinear version. In fact, all my talk can be done bilinearly, but I will not do that so that it's understandable for everyone. Okay, right. So this is the notion of a double Poisson bracket. And if you want some examples, well, a first one that is very naive but still nice is that if you look at the free algebra on 1 generator, so just your polynomial algebra in X here, you can define a double bracket by just saying, okay, on the unique generator X, we say that the double bracket of X with itself, it's X tensor 1 minus 1 tensor X. So as you can see, the cyclic skew symmetry does not impose that the double bracket of an element with itself is zero. Okay, it's not always zero. It's not like a usual Lie bracket because of this cyclicity. And then what is very nice is that once you've defined this on generators, well, you have your derivation rules that allow you to extend that to all elements in your algebra. So this is why I'm saying that it's enough to define a double bracket on generators. A second example is if you take the free algebra on two generators, x and y, then you can say in some way that you make a pairing of x and y. So the double bracket of x and y will tell you that it's just the unit in A tensor A. So this one tensor one, you say that x and y are paired. It's like a symplectic double bracket if you want. And then the double bracket of x with itself is 0, y with itself is 0. This is another example. Okay, so why is this nice? Why is it related to this Concevic-Rosenberg principle that I was telling you about? Because of this theorem here, still in the work of Vandenberg. There are many interesting things in this paper. Okay, and just here at the top there is a reminder if you don't remember. So this AN, it's the nth representation algebra of A. So it's generated by, in some way, matrix entries of matrices representing the elements of A, if you want. And the theorem of Vandenberg is telling you that whenever you have a double bracket, okay, so maybe I can emphasize that, whenever you have a double bracket on A, then for any integer n, the nth representation algebra, it will inherit an antisymmetric biderivation, okay, and it's defined by this rule here. Yeah. So what is the rule? Okay, I will tell you a bit more of that. So the rule is telling you that this thing is, well, basically if you want to compute this Poisson bracket, sorry, it's not yet Poisson, just this operation, this antisymmetric biderivation on generators. So you take an element Aij, an element Bkl, and you want to say, well, what is this thing? Well, the first thing to do to compute this is to say, well, we first compute our double bracket of A and B. Okay, so this is the first operation. We go at the non-commutative level. We compute this double bracket of A and B. And then what we are doing here, okay, so this is a kind of Swidler's notation. We will take the kj element of the matrix representing the first tensor factor and the IL element of the matrix representing the second tensor factor. So a notation that I will introduce now because it generalizes easily is to say that whenever we have computed this double bracket of AB, so this is an element in A tensor A, what I will do next with these indices is just say that to the first factor I will take the kj element, and to the second factor I will take the IL element. So this is a notation that is very convenient to write everything very quickly. And so the theorem of Vandenberg is by defining this operation like that on generators, this extends to an antisymmetric biderivation. And more importantly, and this is really the crux and why this theorem and this theory of double bracket is nice, if your double bracket is Poisson, in the sense that this double Jacobiator that I gave you earlier is always zero, then this bilinear antisymmetric biderivation that I've just introduced is in fact a Poisson bracket. Okay, so you have even more here. Double bracket is Poisson, implies that this operation is a Poisson bracket. And the thing is that why this is true is very transparent from the proof. So I'm omitting the details, but basically, as everything when you have a Poisson bracket, if you want to see that the Jacobi identity is satisfied, you just need to check it on generators. And what's happening is that when you take the Jacobi identity of the generators Aij, Bkl, Cuv, so A, B, C are in A, I, J, K, L, U, V, these are just matrix elements, okay, so they range from 1 to n. Okay. So when you want to compute this, what do you do? Well, the proof tells you that you need to compute the double Jacobiator of ABC, you need to compute the double Jacobiator of ACB, and then you need to put some indices. Okay, so here it's basically very similar to what I did in orange above. So this double Jacobiator of ABC, it's an element in A tensor A tensor A. Okay, so it's a linear sum of pure tensors, and whenever you have a pure tensor, what you say is that, okay, we take the UG entry of the first tensor factor, the IL entry of the second tensor factor, and then the KV entry of the last tensor factor. And then you do a similar rule for the second term here. The important thing being that by my definition, this double Jacobiator is identically zero. So what we are doing here is just take some matrix element of the zero matrix. Okay, so it's identically zero, and this Jacobi identity, the usual one, is indeed zero. Okay, so this is, I mean, really the important thing I would say to keep in mind is this theorem of van den Bergh, because it will be at the basis of all the construction that will appear later. But first, let me convince you that this is not an empty theory that is useless, but that it is really nice. So okay, yes, and there is an invariant subalgebra where you can compute the Poisson bracket as well. Let's not go into that. The important thing is to see that the two previous examples, which were very nice, they are in fact interesting. Why? Because the first case that I gave you earlier, where you had this just double bracket on the free algebra on one variable, okay, so it seemed to be nothing, but when you look at what's happening on representations algebras, well, the thing is that, okay, so here I should say that this is the nth representation algebra here, will be what? Well, it will be basically the coordinate ring of GLN. Okay, and so in fact, what you get is that the Poisson bracket that you induce by the previous theorem on GLN is the usual one that you get. This usual Kirillov-Kostantsovio, if you want, a Poisson bracket on quadjoint orbits that you can in fact take in family on GLN. Okay, so this is the first example. And the second one, where I was telling you that in some way we were pairing X and Y together, well, it's really the case because, okay, so same typo here. If you look at the coordinate ring of the nth representation space of this algebra in the second case, this is the coordinate ring of the cotangent space of GLN. And when you equip this with its canonical Poisson bracket, this is just the Poisson bracket induced by van den Bergh's theory. And so what is very nice is that this second example, again, you could say that it's very elementary, but it extends to an IPAS algebra of quiver. So it's very general, and you can basically understand quiver varieties using that. Okay, so let us move on and try to just define some operations and some linear spaces that will be important to define the cohomology theory later on. Okay, so without going into much detail, what I did earlier was to define a notion of a double bracket. So a double bracket will be a two bracket with my notation of this slide, meaning that it's a linear map that goes from A tensor n to A tensor n, which has a cyclic skew symmetry rule and a Leibniz rule. Okay, so the cyclic skew symmetry, here I have a notation to tell you about. So this sigma means that I'm applying okay, to keep my previous notation, I'm applying the permutation of all factors to 1n to whatever it is applied to. Okay. So the cyclic skew symmetry here means what? It means that, okay, if I'm pushing my A1 to the left and I'm putting it in the last position, then if I do that, I need to push all my tensor factor. Okay, so I'm applying this tau 1 up to n, this permutation to my tensor factor. But I'm also getting a sign here. Okay, so if you remember, for double bracket, we had a double bracket of AB's minus tau 1, 2 of the double bracket of BA. Here it's just a generalization, so with a sign. And then here I'm giving you one Leibniz rule that tells you that in the last argument, the B will come to the left and it will multiply on the left factor. Okay, so here this B, you should really understand this as being a B tensor 1 tensor and so on. So you tensor with many ones. The B multiply on the left factor. And similarly, here the C multiply on the right factor only. And the nice thing is that this unique Leibniz rule, this unique derivation rule defines all the Leibniz rule and derivation rules in all arguments using the cyclic skew symmetry. Yeah, sorry for coughing again. So now that we have these n brackets, what we can do is just take the linear space that is spanned by all these things. So this is my BRAN that I've defined like this. And something technical, but that we will need to do the cohomology theory later on, is to say that we will in some way define zero brackets as being, okay, so this is the very important part here. So in some way, the zero bracket for us are elements in A sharp, where A sharp means that we look at the vector space of A modulo commutators. Yeah. So here, let me emphasize that when we have such an associative algebra A which is fixed, A sharp means that we look at the vector space modulo non-graded commutators. Okay, so it's a vector space. We are not quotienting by the ideal generated by commutators. We are just identifying commutators to zero, and these commutators are not graded. Okay, I need to say that because later on there are also some graded commutators that will come into place. Okay, so this is for n brackets. And in some way, what you should keep in mind is that these n brackets, they are the non-commutative analogs of multilinear vector fields. Okay, that's really the non-commutative analog of my x and a from earlier. Okay, and so what can we do next? Well, here, as I've said, I've defined a non-commutative analog of multi-vector fields. Now I need to define a non-commutative analog in some way of wedges of multi-vector fields. So uh, if it's not clear, you will understand in a minute. I need to give you the definition. So the first thing we do is to consider this, this dir A with mat BB of D. This is the A bimodule of double derivations. Okay, so what are double derivations? It's just some derivations from A to A tensor A. Okay, and the derivation rule is the same as we saw earlier. So here the little a will come to the left and multiply the left factor. So this is the same as A tensor 1 multiplying dB. And then the b will come to the right and multiply on the right tensor factor. So it's taking the form of this one tensor b. Okay, so I'm saying that this is a bimodule because you have a bimodule structure on this there A using the inner derivation rule. Okay, the inner bimodule structure of A tensor A, but it's a bit technical, so let's not worry about that. The important thing is that when you have such an A bimodule, you can consider its tensor algebra of the bimodule over the base algebra A. So this is what we call here this non-commutative multivector field T star A. Okay. So the tensor algebra of this bimodule of double derivations over the algebra A. Okay, and so what I will do now is just tell you the relation between these n brackets and these non-commutative multivector fields. So here is a proposition still due to Vandenberg, and the proposition tells you, and okay, I will not go into the definition really, the important thing is just to remember that there is a well-defined map that takes such a multilinear non-commutative vector field and gives you a n bracket. Okay, and the map is a bit ugly. Okay, so it is there in case you want to see it, but the important thing will be the following. So this map mu n that goes from T star A to n linear brackets, it factors through commutator of T star A. Okay, so here, let me say that the sharp notation here, as I'm saying, it's different from the previous one. Here, the sharp notation is for graded commutators. Okay, so really this thing means that you take elements of T star A modulo the span of all things of the form pq minus 1 to the degree of p times degree of q, qp. Okay. Okay. Right. So here is the thing is that this mu n, in general, in many nice cases, for example, for free algebras, for path algebra of quivers, and so on and so forth, these mu n, they are all isomorphisms in general. And in that case, the two cohomology theories that I will define later will be the same. But when these mu n's are not isomorphism, there is something interesting, and this is what we will see. Oh, yes, and just one last thing before I continue. So for double brackets, we call them differentials if they are the image of some non-commutative bivector field under the map mu2. Okay. So for example, the double bracket on kx that I gave you earlier, okay, it is differential for this p that is given there. Okay. And important thing is that when you truncate this kx, it is no longer differential. Okay, so this is something that is very important and that will be nice as we will see later. Okay, so what are we going to see now that I've introduced the main characters in some way for the story? So it took some time, but now we will be able to understand things. So what we need to keep in mind is the following. So in the standard case for Poisson cohomology, what you could do was to say, well, either we define the Poisson cohomology using the Chevalier-Eilenberg cohomology of the Poisson algebra A, using its Poisson bracket, or we could define the Poisson cohomology of A using here this operation d pi, which was obtained from the Skottoner-Noyes bracket of the bivector pi with every element. And whatever you were doing, this would give you the exact same theory. And now what we want to do is to try to see what is going on for those at the non-commutative level. Okay, so let me maybe say the first thing that I will do is this middle point here. So the middle point will be to define some double Poisson cohomology that is due to Pichereau and van der Weyer. And they define this as being in some way the non-commutative analog of this operation here in the middle. Yeah. So it will be something very similar defined on multi-vector fields modulo graded commutators. Then the second thing that I will tell you about is the new completed version that I did with Daniele Valeri here, where it's basically a non-commutative version of, in some way, the Chevalier-Eilenberg cohomology for the Poisson algebra. And then what we will see is that, okay, we have a map mu n going from the Pichereau-van der Weyer double Poisson cohomology to this new completed double Poisson cohomology. And, well, this linear map exists when the double Poisson bracket is differential. So it means it's a mu2 of something. Yeah. So as a comment for experts, maybe, so as we will see, the formula that I will present is reminiscent to some general construction of Sophie Chemla about double linear algebra cohomologies. And interestingly, the approach for two that we took with Daniele Valeri, there is something a bit more general based on some Skottoner-Noyes bracket on this BRA at operation that has been done by Zheng and Tan. So they shared with us their paper. Unfortunately, it's not available on the arXiv. So I hope it will be published soon, or maybe they will put it on some open repository so that everyone can enjoy their work. Okay, so as I was saying, what we want now is to look at the first approach of Pichereau and van der Weyer. And as I was saying, it's based on some kind of non-commutative version of the Skottoner-Noyes bracket but here on non-commutative multivector fields. So how does it work? Well, I mean, here there is a general theorem. Let's not look at everything. What is important for us is the last part here, which tells us that T star AN, so remember T star A means it's a non-commutative multivector field. The sharp here symbols means that we take them modulo graded commutators. And what is important for us is that this graded vector space inherits a graded E bracket from a construction here of Vandenberg. Okay, this is the important thing. This is this SN bracket. This is a graded E bracket on this vector space. Okay, so why is it nice to have this operation? Well, because when you have a double bracket which is differential, so remember it means a double bracket which is mu2 of something, some p. When you have such a mu2 p, you can, thanks to this theorem, say that you are Poisson, meaning that this double Jacobiator is identically zero. This is the case if and only if, under this new operation that I've given there, under this new operation, the bracket of P with itself is zero. So again, this is very reminiscent of the classical theory where you have a bivector which is Poisson if and only if its cotton Aeronoids with itself is zero. Here it's the same thing. Okay, but so why is that important? Because no, this is general theory, this is general result, nothing very important here to this specific case. When you have a graded bracket of degree 1 and an element P of degree 2 whose bracket with itself is 0, you get a differential on this graded algebra. And so this is really what Pichereau and Weyer have done. They've said that, okay, we can define this dP as the bracket of P with anything. This curves to 0. And so when we look at the complex T star A modulo graded commutator with this differential, we look at the corresponding cohomology theory, we get the so-called double Poisson cohomology. Right. So this is a first non-commutative cohomology theory. And what is nice is that this sits well within this conservate-Rosenberg principle that wants you to be able to induce a usual structure from a non-commutative structure. So here the first two lines are just to remember what I've said in the previous slide, that you have such a double Poisson cohomology. And what Pichereau and Van der Weyer has shown is that, well, I can directly highlight what is important for us, is that we have a linear map here in cohomology between what? Between their double Poisson cohomology that I've just introduced, and here this PHAN. What is PHAN? Just remember, this is what I said earlier. By Vandenberg's result, a double Poisson bracket induces a Poisson bracket. This Poisson bracket is in fact defined from a bivector. This is this trace P that is written there. Okay, so with trace P, which is a Poisson bivector, on the nth representation algebra AN, what we can do, well, we can look at the corresponding D trace P, meaning that you take the usual commutative Scotton Aeronoids bracket of trace P with anything, and on this vector space of multilinear vector fields on AN, you get such a square zero differential, which defines the Poisson cohomology of AN. So you get such a map here in red, which is very nice. And what is also very nice, and this is illustrated in this diagram, is that in fact, because whenever you induce, okay, I will say that later on, but whenever you induce from some element of T star A sharp, an element in multivector fields on AN, these elements will always be GLN invariant. So in fact, this map that I've given to you is also mapped into the GLN invariant part of the Poisson cohomology. And this restricts to the Poisson cohomology of the GLN invariant part of the algebra. So this is what I've written here, that the map in fact goes to the Poisson cohomology of the GLN invariant element in AN. Okay, and here, sorry, there is a typo, so I didn't change that on the slide. I'm very sorry, but all these little n should be a capital N because, as I've told you, I'm giving you a baby version for the presentation so that everything is a bit easier to follow. So in the word diagram below as well, all the little n should be capital N. Okay, so what next? Well, okay, here, I mean, obviously after the paper it was nice because there was a notion of a non-commutative Poisson cohomology, but the thing is that the computation of cohomology groups that I made are a bit long, and more importantly, the second point here, the cohomology theory is not always defined. Okay, because remember, to define this double Poisson cohomology here, I needed my double bracket to be of the form mu2 of p. So I needed this double bracket to be in the image of mu2. But so if it's not, for example, if all mu n's are not isomorphism, it could happen that the double Poisson bracket is not mu2 of something. And then you don't have a double Poisson cohomology. So this is something that we will take care of now. Define a cohomology theory for double Poisson brackets in general settings, and then there will be a Chevalier-Eilenberg version of that coming on under representation functors. Okay, so maybe this will be the last thing that I will talk about, and the final remarks can be quite long, so I will skip them altogether. So here is the maybe most important slide for me, but that you should not take too much time to look at. This slide is just telling you that on this vector space BRA of all n-linear double brackets, which is completed in degree 0 by elements of A modulo commutators, on this BRA hat, there is, with this definition, an operation which is a square zero differential. So at the moment, you don't know it's a square zero differential. You just know that I'm defining something. Okay, so I mean, let me just take a 1 minute on this definition so that you see that it's not coming out of nowhere. So here, in some way, the first line is basically telling you that if you were in the commutative story and you want to take the differential of an element of your Poisson algebra A, then you just take the Poisson bracket of this element with anything else as being your new operation. This is more or less what we have here. It's just that we need to multiply because a double Poisson bracket, now that I'm writing with square bracket to be sure that you see that it's not the same as any other operation. This operation is in A tensor A, so if we want to get an element in BR1, which are derivations, we need to multiply the two elements. And then in higher degrees, basically what is the formula saying? Well, if you have some time, just compare that to the usual formula for the Scott-Oniron-Noyes bracket in the commutative setting. And you will see that basically the Scott-Oniron-Noyes bracket is saying you that, okay, you take the bracket of one of the operations, so here my double Poisson bracket, and then the other one, or up to some sign, you do the opposite. You take the second operation and then the first one. And here, as you see, well, because we are having elements, so when you get a D of something which is an n bracket, you get an n+1 bracket, so it's an operation on A to the tensor n+1. Okay, so this is why there are a couple of identity elements that should be put. And then because all my operations have some cyclic skew symmetry, I have these sigmas here that are basically telling me that I need to skew symmetrize everything. So this sigma here means that I have 2 of 1 up to n+1. Okay, because I have as many elements as that. Okay, so there is a general construction like that. Okay, the theorem is the following. This operation is a square zero differential on these vector space of an inner bracket. And I mean, this is really a direct computation. I will not go into that. The important thing is that now, because you have some vector space, a graded vector space, this BRA, so you can see it as a complex with this differential, you can consider the corresponding cohomology theory. And this cohomology theory is what we call double Poisson cohomology in our work with Daniele. Okay, so what? So what is very nice is that when this double bracket here is mu2 of something, so when we are in the previous setting of Pichereau van der Weyer, then the mu and maps define a morphism of complexes between T star A sharp, so where the Pichereau van der Weyer differential was defined, and our complex on n brackets, this BRA. And so what is very important is this thing that we get a k-linear map in cohomology going from the Pichereau van der Weyer double Poisson cohomology to the new completed one. Yeah. And as you see, I mean, if you look at everything on complexes, there are some signs appearing, but they are not important when you go to the corresponding cohomology. Okay, and in particular, well, when all these mu n's are isomorphism, so if all the vertical maps are isomorphism, which happens, for example, for free algebras or path algebra of quivers and so on, then the two cohomology theories are the same. Right. So I will skip this so that I have some time for some examples, but just if you want to have some nice formula, here we were able to rewrite a very nice formula for this differential, which is inspired by the cohomology theory of double Lie-Reinhardt algebras defined by Sophie Schemla. Okay, so now let's try to wrap up everything and understand why what we've defined is related to the Kontsevich-Rosenberg principle. So the important thing here for the notation is what I told you earlier, is that the Poisson bracket, according to Vandenberg, at this form, okay, meaning that when you wanted to compute the Poisson bracket induced by a double bracket on Aij and Bkl, what you needed to do is compute the double bracket of AB and then be smart and put the indices on the two tensor factors in a nice way, Kj, Il, like this. The theorem below, it's basically a generalization of that. Okay, so I don't need to go into the detail, but the theorem below is just telling you that whenever you have a n bracket like this, sorry, a k bracket in this case, you can uniquely extend this k bracket to an operation to a k-linear multivector field on the nth representation algebra, which will also be GLN invariant. And the formula is very explicit. Yeah. And so why is that nice? Because remember, we have constructed a new double Poisson cohomology. And now with that map, we can map the complex of the new double Poisson cohomology to the complex of xkan, used for the usual Poisson cohomology if you use the Chevalier-Eilenberg point of view. So you could ask yourself, well, are the two related? Do you have a map in cohomologies? And yes. The point is that if you do things carefully, you see that you get a map in cohomology between, okay, I've not been emphasizing the correct map. The important first map is that you have here this map from the completed double Poisson cohomology of A for any double Poisson bracket to the Chevalier-Eilenberg cohomology of the induced Poisson bracket on AN for any n, so on any representation space. And then the second thing that I've put in this red square is saying that this in fact goes to GLN invariance elements and the Chevalier-Eilenberg cohomology on the Poisson algebra of GLN invariance elements. And the proof is, I mean, extremely long, but it's basically just the commutativity of a diagram. So all the theorem that I'm giving you, the proofs are tedious, but it's just some playing with the definition and trying to see where it's heading. Okay. And so, yes, one last thing here is just a corollary saying that so there was this original construction of Pichereau and van der Weyer here. This double Poisson cohomology of Pichereau-van der Weyer was mapped to the usual Poisson cohomology of AN using the Schrödinger noise formalism. And what I've said now is that, in fact, we have a map from the Pichereau-van der Weyer double Poisson cohomology to a new double Poisson cohomology. In the case, we have a non-commutative bivector defining the double Poisson bracket. And more importantly, this map goes to the Chevalier-Eilenberg cohomology on the nth representation algebra. And what is very nice is, as you could guess, this gives you a commutative diagram. And the commutative diagram restricts on the right to GLN invariant elements. Okay. And I will not have much time for examples. Okay, so let me try to wrap up and just say one thing. Okay, one important computation that we've made with Daniele. And the computation is the following. So whenever you are on the free algebra on, let's say, L generators, okay, if you fix a skew-symmetric non-degenerate matrix, so non-degenerate in the sense invertible matrix, this C, then you can uniquely define a double Poisson bracket using this matrix by saying that, okay, the double Poisson bracket on any two generators, Ui, Uj, is 1 tensor 1 multiplied by the factor Cij here. So the ij element of the matrix C. And what we've been able to do is to compute this double Poisson cohomology in all cases. Okay. So whenever we have such a C, we can compute the double Poisson cohomology. And I mean, it's a technical proof, so I will share my site for those that are interested. But the point is that, and this is very funny because it's really like the usual theory. So when you have a non-degenerate Poisson bracket, which is in fact a symplectic form, you can map it to the Durham cohomology. Okay. And basically there you can say, okay, everything that is closed is exact. And this is basically the same thing that we have here. We can just map everything to using some homotopy operator to see that everything closed is in fact the D of something. Okay, so it must be a cobordary. Okay, so I think, yes, it's better to stop here. So I had some final remarks about some generalization of the construction, but I mean, it's better if you just understand what I've said now, and if we don't spend too much time on many variations of the theory. So please feel free to drop me an email or ask me question now if you want to know more, but otherwise, I will just stop now. So thank you for listening.
Okay, so thank you very much for a very interesting talk. Can we thank Maxime in the usual way? Are there any questions or comments anyone wants to make? No? Okay, well, I hope people will take up Maxime's invitation to contact him with any detailed questions.
Yeah.
So thank you very much again for your interesting talk.
Thank you, and thank you, everybody. And don't forget about this launch of the Journal of Non-Associative Structures today. Thank you all.